In October 2017, astronomers discovered something that shouldn't exist. A dark, elongated object tumbling through our solar system at impossible speeds, following a trajectory that defied everything we thought we knew about celestial mechanics. They called it Oumuamua, Hawaiian for scout or messenger, and for 3 years it remained the most mysterious visitor our solar system had ever encountered. But then, in the summer of 2020, something even stranger appeared on our telescopes. Something that would make Oumuamua look ordinary by comparison. Something that would force us to rewrite the textbooks on interstellar objects and confront possibilities we never dared to imagine. Tonight, we're diving deep into the mystery of Borisov, the second confirmed interstellar visitor, and how its discovery has completely transformed our understanding of what's really traveling between the stars. Because while Oumuamua left us with questions, this new arrival brought answers that are far more unsettling than the mysteries themselves. If you're finding comfort in these gentle explorations of cosmic mysteries, I'd be grateful if you'd consider subscribing and giving this video a like. The visuals are here to guide you, but feel free to close your eyes. Let your imagination drift among the stars and allow these cosmic puzzles to wash over your thoughts like distant starlight. Also, I'd love to know where you're listening from tonight. Drop your time and location in the comments below. Let's begin. What makes an object from another star system so extraordinary isn't just that it's traveled impossible distances to reach us. It's that these visitors carry with them the chemical signatures, the physical properties, and the evolutionary history of alien solar systems. They're like cosmic time capsules, preserving secrets from stellar neighborhoods we may never be able to visit directly. When Oumuamua first appeared, racing through our solar system at over 87,000 kilometers per hour, it immediately stood out as something fundamentally different. Its trajectory was hyperbolic, meaning it was moving too fast to be gravitationally bound to our sun. It had come from somewhere else, and it was heading back out into the void of interstellar space. But that wasn't the strangest part. As telescopes around the world trained their instruments on this cosmic wanderer, they revealed an object unlike anything we'd ever seen. Oumuamua was roughly 400 meters long, but only about 40 meters wide, giving it an elongated cigar-like shape that was 10 times longer than it was wide. No natural object in our solar system has proportions even close to this extreme. The mystery deepened when astronomers tried to determine what Oumuamua was made of. Unlike comets, which develop bright tails as they approach the sun and their ices sublimate into space, Oumuamua showed no signs of outgassing. No tail, no coma, no visible jets of material streaming from its surface. It appeared to be a solid, rocky object, more like an asteroid than a comet. Yet as careful observations continued, something even more puzzling emerged. Oumuamua was accelerating away from the sun faster than gravity alone could account for. This non-gravitational acceleration was subtle but unmistakable, detected by multiple independent teams of astronomers using different methods and instruments. For comets, such acceleration is perfectly normal. As the sun heats a comet's icy surface, jets of sublimating gas create a rocket-like effect, pushing the comet slightly off its purely gravitational trajectory. But Oumuamua showed no visible signs of this outgassing process. So what was causing it to speed up? The scientific community found itself grappling with several uncomfortable possibilities. Perhaps Oumuamua was composed of some exotic material we'd never encountered before. Maybe it had an unusual internal structure that allowed it to outgas in ways our instruments couldn't detect. Or perhaps, as some researchers cautiously suggested, it wasn't a natural object at all. This last possibility sent ripples of excitement and controversy through the astronomical community. Dr. Avi Loeb of Harvard University proposed that Oumuamua's unusual properties could be explained if it were an artificial object, perhaps a light sail created by an extraterrestrial civilization. The idea was provocative, scientifically rigorous, and deeply unsettling to many of his colleagues. The debate raged for months. Papers were published, conferences were held, and astronomers around the world scrutinized every pixel of data collected during Oumuamua's brief passage through our solar system. But by the time the scientific community had fully mobilized to study this interstellar visitor, it was already too faint and too far away for detailed follow-up observations. Oumuamua had given us a tantalizing glimpse of the objects that drift between the stars, but it left us with more questions than answers. Was it representative of typical interstellar objects, or was it an anomaly? Were there more such visitors passing through our solar system undetected? And perhaps most importantly, what could these cosmic messengers tell us about the formation and evolution of planetary systems beyond our own? The answers to these questions would have to wait, but not for long. On August 30th, 2019, an amateur astronomer named Gennady Borisov was conducting his regular survey of the night sky from his observatory in Crimea. Using a telescope he had built himself, Borisov spotted what appeared to be a new comet in the constellation Lynx. At first, it seemed like an ordinary discovery, the kind that amateur astronomers make several times each year. But as professional observatories around the world began tracking this new object, designated Tuai Borisov in honor of its discoverer, something remarkable became apparent. Like Oumuamua before it, this comet was following a hyperbolic trajectory. It was another visitor from interstellar space. Unlike Oumuamua, however, Tuai Borisov looked and behaved exactly like the comets we know from our own solar system. As it approached the Sun, it developed a classic cometary coma, a fuzzy envelope of gas and dust surrounding its nucleus. Spectroscopic analysis revealed familiar chemical signatures: water vapor, carbon monoxide, and other molecules we routinely detect in solar system comets. In many ways, Tuai Borisov was reassuringly normal. It had a nucleus roughly 1 kilometer in diameter, well within the range of typical comets. Its composition appeared to match what we'd expect from objects formed in the outer regions of planetary systems, where temperatures are cold enough for water and other volatiles to freeze into solid ice. But this normalcy was precisely what made Tuai Borisov so revolutionary. By comparing the properties of these two interstellar visitors, astronomers began to piece together a new picture of what exists in the space between stars. Oumuamua, with its bizarre elongated shape and mysterious acceleration, might indeed be an anomaly. But Tuai Borisov suggested that most interstellar objects are probably quite ordinary, formed through the same processes that create comets and asteroids in our own solar system. This realization led to a profound shift in how we think about planetary formation and stellar evolution. If interstellar space is filled with objects like Tuai Borisov, objects that were presumably ejected from their birth systems during the chaotic early phases of planetary formation, then the exchange of material between star systems might be far more common than we ever imagined. Consider what this means for the distribution of life in the universe. Every planetary system goes through a violent adolescence, as gravitational interactions between forming planets fling countless asteroids and comets into interstellar space. These ejected objects carry with them the chemical fingerprints of their birth systems, including, potentially, the organic molecules, and even the microbial life that might have evolved in those distant worlds. The implications are staggering. Rather than being isolated islands of matter and energy, stellar systems might be connected by vast streams of ejected material, creating a kind of galactic ecosystem where the building blocks of life can migrate between stars over cosmic timescales. But Borisov revealed something even more significant about these interstellar wanderers. Detailed spectroscopic observations showed that its composition was subtly different from solar system comets. The ratios of certain isotopes, the relative abundances of different molecules, and the overall chemical signature all pointed to formation conditions that were distinct from those in our own stellar neighborhood. This was the first direct evidence that different stellar systems have genuinely different chemical environments, different histories of element formation and planetary assembly. Borisov was carrying within its frozen nucleus a record of stellar nucleosynthesis, planetary formation, and chemical evolution that occurred around a different star, under different conditions, billions of years ago. The discovery transformed our understanding of galactic chemical evolution. Rather than relying solely on distant spectroscopic observations of other star systems, we now had physical samples of material from those systems, delivered directly to our doorstep by the Cosmic Postal Service of Gravitational Dynamics. As Borisov continued its journey through our solar system, telescopes around the world worked frantically to extract every possible piece of information from this cosmic messenger. The Hubble Space Telescope captured stunning images of the comet's coma and tail, revealing structures and asymmetries that provided clues about the nucleus's composition and rotation. Ground-based observatories measured the polarization of reflected sunlight, the thermal emission from heated dust grains, and the velocities of gas molecules streaming from the comet's surface. Each observation added another piece to the puzzle of interstellar object populations and their role in connecting stellar systems across the galaxy. But perhaps the most significant revelation came from comparing Borisov's behavior to that of Oumuamua. While Borisov behaved exactly as expected for a comet, developing outgassing jets that created measurable, non-gravitational accelerations, Oumuamua's mysterious acceleration remained unexplained. The contrast between these two objects highlighted just how unusual Oumuamua truly was, and reinforced the possibility that our first confirmed interstellar visitor might represent something entirely unprecedented in our experience. This realization has profound implications for our search for evidence of extraterrestrial intelligence. If most interstellar objects are like Borisov, natural bodies ejected from forming planetary systems, then objects like Oumuamua stand out as potential anomalies worthy of special attention. The discovery of a second interstellar object that behaved normally made the first one's abnormal behavior even more significant. But the story of interstellar visitors is just beginning. Advanced sky surveys like the Catalina Sky Survey, Linear, and the upcoming Legacy Survey of Space and Time are expected to detect dozens or even hundreds of interstellar objects over the next decade. Each new discovery will add to our understanding of the material that flows between star systems, the processes that eject objects from planetary systems, and the chemical diversity that exists throughout our galaxy. As we prepare to welcome these cosmic messengers, we're also developing new technologies and strategies for studying them. Rapid response space missions are being designed to intercept and study interstellar objects during their brief passages through our solar system. Next-generation telescopes will be able to detect these visitors sooner and study them in greater detail than ever before. The age of interstellar archaeology has begun, and we're only just starting to read the cosmic library that's been delivered to our solar system by billions of years of gravitational dynamics and stellar evolution. The discovery of multiple interstellar visitors has fundamentally changed how we view our solar system's place in the cosmic community. We're no longer looking at isolated pockets of matter orbiting distant stars, but rather at a vast interconnected web where material flows freely between stellar neighborhoods, carrying with it the stories of worlds we may never see directly. What's particularly fascinating about this new perspective is how it reshapes our understanding of planetary system evolution. Every star system we observe, from the nearest red dwarfs to the most distant sun-like stars, goes through similar phases of violent reorganization during its youth. Massive planets migrate inward and outward, their gravitational influence flinging smaller bodies into the interstellar void like cosmic billiard balls scattered across an impossibly large table. These ejection events aren't rare occurrences. Computer simulations suggest that for every object that remains gravitationally bound to a star, dozens or even hundreds are expelled into interstellar space. This means that the volume between stars is filled with a sparse but vast population of wandering worlds, fragments of shattered planetesimals, and frozen remnants of ancient comets that once called distant solar systems home. The implications for astrobiology are profound and deeply unsettling. If microbial life can survive in the frozen interiors of comets and asteroids, as some research suggests it might, then these interstellar wanderers could be carrying living cargo between star systems. A single impact event billions of years ago could have launched not just rock and ice into space, but entire ecosystems preserved in cosmic amber, waiting to seed new worlds with the genetic legacy of their parent system. This possibility transforms panspermia from a fringe hypothesis into a testable scientific theory. Rather than requiring the deliberate intervention of advanced civilizations, life could spread naturally throughout the galaxy through the ordinary processes of planetary formation and gravitational dynamics. Every comet impact, every asteroid collision, every close encounter with a massive planet becomes a potential chapter in a vast biological story that spans star systems and geological epochs. But the traffic isn't one way. Our own solar system has undoubtedly contributed its share to this interstellar diaspora. During the late heavy bombardment, when massive impacts scarred the surfaces of the inner planets, countless fragments of Earth, Mars, and Venus were launched into interstellar space. These pieces of our homeworlds are now scattered throughout the galaxy, carrying with them the chemical signatures of terrestrial oceans, Martian geology, and perhaps even fossilized evidence of early life. The thought is both humbling and exhilarating. Somewhere in the space between stars, fragments of the ancient Earth are tumbling through the cosmic void, preserving samples of our planet's earliest biosphere. These terrestrial meteorites might one day impact distant worlds, delivering the building blocks of Earth-based life to alien shores. We are already, in a very real sense, a spacefaring species, even if we don't yet have the technology to follow our scattered remains to their distant destinations. This cosmic exchange program operates on timescales that dwarf human civilization. Objects ejected from our solar system 4.5 billion years ago are still journeying between the stars, carrying within them the fossilized memories of our sun's violent youth. Meanwhile, visitors like Oumuamua and Borisov bring us samples from stellar systems that may have formed and evolved under completely different conditions than our own. The chemical analysis of Borisov revealed subtle but significant differences from solar system comets. The ratios of carbon to nitrogen, the isotopic signatures of water ice, the trace abundances of rare elements all pointed to formation in a stellar environment with a different nucleosynthetic history than our own. These weren't just alien rocks, they were alien chemistry, preserved samples of stellar evolution pathways we can only guess at from distant spectroscopic observations. Each interstellar visitor is essentially a free sample return mission from another star system, delivering to our laboratories material that we could never hope to reach with our current technology. The nearest star is over 4 light-years away, requiring thousands of years of travel even with our most advanced spacecraft concepts. Yet these cosmic messengers bridge that impossible gap, bringing us direct physical evidence of conditions around other stars. The discovery that such objects exist in detectable numbers has triggered a renaissance in interstellar object research. Astronomers are developing new search strategies, refined detection algorithms, and rapid response protocols for studying these brief visitors. The window of opportunity is always narrow, typically lasting only weeks or months as the objects pass through the inner solar system, where our telescopes can observe them most effectively. Future space missions are being designed specifically to intercept interstellar objects. Concepts like the European Space Agency's proposed Comet Interceptor mission could be adapted to rendezvous with these visitors, using flexible trajectories and advanced propulsion systems to match their hyperbolic paths. Such missions would allow us to study interstellar material with the same detail we apply to asteroids and comets in our own solar system. The technological challenges are immense. Interstellar objects travel at velocities that make rendezvous missions extremely difficult with current propulsion technology. Their trajectories are often not well determined until they're already past closest approach to the Sun, leaving little time for mission planning and spacecraft deployment. Yet the scientific rewards would be extraordinary, potentially revolutionizing our understanding of planetary formation, stellar evolution, and the distribution of life in the universe. Advanced ground-based telescopes are also being optimized for interstellar object detection and characterization. The upcoming Vera C. Rubin Observatory will scan the entire visible sky every few nights, identifying moving objects with unprecedented sensitivity. Its sophisticated data processing algorithms will be able to distinguish the subtle signatures of interstellar visitors from the much more numerous population of solar system objects. These surveys will likely reveal that interstellar objects come in a vast range of sizes, compositions, and origins. Some may be pristine samples of the interstellar medium itself, chunks of molecular cloud material that never experience the heat and pressure of stellar formation. Others might be fragments of disrupted planets, torn apart by tidal forces during close encounters with massive stars or stellar remnants. The diversity promises to be staggering. We might discover objects composed of exotic ices that can only form in the extreme cold of interstellar space, or rocky fragments bearing the chemical signatures of supernova explosions that occurred billions of years ago. Each new discovery will expand our understanding of the processes that shape matter on galactic scales. But perhaps the most intriguing possibility is that some of these objects might not be natural at all. The unusual properties of Oumuamua, contrasted with the perfectly normal behavior of Borisov, suggest that our first confirmed interstellar visitor might represent something unprecedented in our experience. Its extreme elongation, mysterious acceleration, and apparent lack of outgassing continue to challenge conventional explanations. If advanced civilizations exist in our galaxy, and if they've developed technologies for interstellar travel or communication, then some fraction of the objects passing through our solar system might be artificial in origin. Light sails, automated probes, or even derelict spacecraft could masquerade as natural interstellar objects until subjected to detailed scientific scrutiny. The prospect is both thrilling and sobering. We might already have encountered evidence of extraterrestrial technology, evidence that passed through our solar system and returned to interstellar space before we fully understood what we were seeing. The brief observation window for interstellar objects means that we might have missed crucial details that could have revealed the artificial nature of these visitors. This possibility has transformed the search for extraterrestrial intelligence from a passive listening exercise into an active archaeological investigation. Every new interstellar object detection becomes an opportunity to test the hypothesis that some of these visitors might be more than mere rocks and ice. Advanced analysis techniques, including radio monitoring, infrared spectroscopy, and high-resolution imaging, are now standard protocols for studying these cosmic wanderers. The implications extend far beyond the search for alien technology. If interstellar objects are common enough to be detected regularly by our surveys, then the space between stars is far more dynamic and interconnected than we previously imagined. The galaxy becomes not a collection of isolated stellar systems, but a vast ecosystem where matter, energy, and potentially life itself flow freely between distant worlds. This interconnectedness operates on timescales that span the entire history of the galaxy. Objects ejected from stellar systems billions of years ago are still traveling between the stars, carrying with them the frozen archives of ancient worlds. Meanwhile, newly formed planetary systems are launching their own contributions to this cosmic diaspora, adding fresh material to the interstellar inventory. The chemical evolution of the galaxy becomes a much more complex and interesting process when viewed through this lens. Rather than relying solely on stellar nucleosynthesis and supernova explosions to distribute heavy elements throughout space, we must also consider the role of interstellar objects in transporting processed materials between stellar environments. A comet ejected from a metal-rich system around an old star could deliver its cargo of heavy elements to a young stellar nursery, influencing the composition of newly forming planets in subtle but significant ways. This cosmic recycling program operates with an efficiency that would make any environmental engineer weep with envy. Consider the mathematics of galactic mixing over billions of years. Every cubic parsec of interstellar space contains a sparse but measurable population of these wandering remnants, each one a data point in a vast experiment in chemical evolution that has been running since the first stars began to shine. The discovery of Borisov didn't just confirm that interstellar objects exist, it revealed something far more profound about the nature of planetary system formation itself. The comet's chemical composition, while distinctly alien, fell within ranges that our models of stellar nucleosynthesis could explain. This wasn't random cosmic debris, but material that had been processed through the same fundamental astrophysical mechanisms that operate throughout the galaxy. Yet subtle differences in isotopic ratios told a more nuanced story. The deuterium content of Borisov's water ice was slightly elevated compared to solar system comets, suggesting formation in a stellar environment with a different history of stellar evolution and element production. The carbon monoxide abundance was higher than expected, indicating preservation in an environment colder than the outer regions of our own stellar nursery. These aren't just academic curiosities. They're direct measurements of the conditions that prevailed during planetary formation around other stars, data that we could never hope to obtain through remote observation alone. When we analyze the spectral lines from distant stellar systems, we're looking at the integrated light from entire regions of space, averaged over vast volumes and complex geometries. But interstellar objects deliver individual samples, pristine archives of specific formation environments that we can study grain by grain in our laboratories. The implications for understanding planetary habitability are staggering. If we can decode the chemical signatures preserved in these cosmic messengers, we can begin to map the diversity of stellar environments throughout our galactic neighborhood. Some regions might be rich in the organic precursors necessary for life, while others might be dominated by refractory materials that would make biological evolution challenging. More intriguingly, we might discover chemical signatures that have no natural explanation within our current understanding of stellar evolution. Unusual isotopic ratios, unexpected molecular combinations, or trace abundances of elements that shouldn't exist in the quantities we observe could point to processes we haven't yet recognized or understood. The search for such anomalies has become a cottage industry within the astronomical community. Every new interstellar detection triggers a cascade of follow-up observations as researchers around the world compete to extract the maximum scientific value from these brief visitations. Spectrographs measure the wavelengths of light reflected and emitted by these objects, revealing their chemical composition. Photometric surveys track their brightness variations, providing clues about their rotation, shape, and surface properties. Advanced polarimetry techniques can reveal details about the microscopic structure of dust grains in cometary comae, while thermal infrared observations probe the temperature distribution across rocky surfaces. Radio telescopes listen for any artificial signals that might be emanating from these visitors. Just in case we're dealing with something more than natural space debris, the data analysis pipeline for interstellar objects has become one of the most sophisticated in astronomy. Machine learning algorithms sift through terabytes of observational data, searching for patterns and anomalies that might escape human notice. Statistical techniques borrowed from particle physics help separate genuine signals from instrumental noise and systematic errors. Yet for all our technological sophistication, we're still fundamentally limited by the physics of detection. Most interstellar objects are discovered when they're already well inside the solar system, having spent months or years approaching the sun undetected. By the time our automated surveys identify them as unusual, they're often racing away from us at velocities that make detailed study challenging. This observational bias means we're probably missing the majority of interstellar visitors entirely. Objects that pass through the outer solar system without coming close to the sun remain too faint for our current generation of telescopes to detect. We're essentially standing at the bottom of a gravitational well, watching only those cosmic messengers that happen to fall deep enough into our stellar neighborhood to become visible. The true population of interstellar objects streaming through local space is likely orders of magnitude larger than what we've observed directly. Computer simulations suggest that at any given moment, there might be dozens of interstellar visitors within the orbit of Neptune, invisible to our instruments, but carrying within them the frozen libraries of distant worlds. This hidden population represents one of the greatest untapped resources for understanding galactic evolution and the prevalence of planetary systems throughout the Milky Way. Each undetected visitor is a lost opportunity to sample the chemical inventory of another stellar neighborhood, to test our theories of planetary formation against the physical evidence of alien worlds. Future technological developments promise to dramatically expand our ability to detect and study these cosmic wanderers. Next-generation space telescopes operating in the infrared will be sensitive to the thermal emission from interstellar objects, allowing detection at much greater distances than is possible with reflected sunlight alone. Advanced coronagraphs might be able to spot these visitors while they're still in the outer solar system, providing years rather than weeks for detailed observations. Ground-based facilities are also evolving rapidly. The Vera C. Rubin Observatory will begin operations in the coming decade, promising to revolutionize our ability to detect moving objects throughout the solar system. Its unprecedented combination of wide field of view, high sensitivity, and rapid cadence will likely increase the detection rate of interstellar objects by orders of magnitude. But perhaps the most exciting developments are happening in spacecraft technology. Concepts for rapid response interstellar object missions are advancing from science fiction to serious engineering studies. Solar sails and ion drives could enable spacecraft to match the hyperbolic trajectories of these visitors, allowing close-up study of material from other star systems. The engineering challenges are formidable. Interstellar objects often follow trajectories that are poorly determined until they're already past closest approach to the Sun. Mission planners would have only weeks or months to design trajectories, prepare instruments, and launch spacecraft capable of rendezvousing with targets moving at tens of kilometers per second. Yet the scientific rewards would be extraordinary. A successful rendezvous mission could return samples of interstellar material to Earth for detailed laboratory analysis. We could study the crystal structure of alien minerals, search for organic compounds that might have formed in other stellar environments, and perhaps even discover fossilized evidence of extraterrestrial life preserved in cosmic ice. The prospect of holding fragments of alien worlds in our hands, of conducting chemical analyses on material that formed around other stars billions of years ago, represents a paradigm shift in how we study the universe. Rather than relying solely on remote sensing and theoretical models, we could begin to practice hands-on galactic archaeology, piecing together the history of stellar evolution from physical evidence delivered directly to our solar system. This transformation from passive observation to active sample collection would mark a new chapter in humanity's relationship with the cosmos. We would no longer be limited to wondering about the conditions that exist around other stars. We could measure them directly, comparing the chemical signatures of different stellar environments with the precision and detail that only laboratory analysis can provide. The psychological impact of such discoveries might be even more profound than the scientific insights they provide. Holding a piece of another world, knowing that it formed around a different star under alien skies, would connect us to the broader galactic community in ways that no amount of theoretical knowledge could match. These wouldn't be abstract concepts from textbooks, but tangible evidence that we share the galaxy with countless other worlds, each with its own unique history and evolutionary trajectory. But the story of interstellar visitors is still being written. Each new detection adds another chapter to our understanding of how matter flows between stellar systems, how chemical evolution proceeds on galactic scales, and what role these cosmic messengers might play in connecting distant worlds. The next interstellar object could arrive tomorrow, bringing with it chemical signatures we've never encountered, physical properties that challenge our understanding of planetary formation, or perhaps even evidence that we're not alone in the universe. The transformation in our perspective has been remarkable. Just a few years ago, interstellar objects were theoretical curiosities, predicted by models but never observed directly. Today, they're recognized as a fundamental component of galactic ecology, bridges that connect stellar systems across the vast emptiness of space. Tomorrow, they might become our first direct contact with the products of alien evolution, chemical laboratories that formed under foreign suns and traveled across impossible distances to reach our waiting instruments. As we stand on the threshold of this new era of interstellar archaeology, we find ourselves confronting questions that seemed purely academic just a generation ago. What can these cosmic messengers tell us about the prevalence of life in the universe? How diverse are the chemical environments that exist around other stars? And perhaps, most intriguingly, how many of these visitors might represent something more than natural debris, artifacts of technologies and civilizations that we're only beginning to imagine? The answers lie hidden in the darkness between stars, encoded in the chemical signatures of wandering worlds that carry within them the frozen memories of alien suns. Each new detection brings us closer to deciphering these cosmic messages, to understanding our place in a galaxy that is far more interconnected and dynamic than we ever dared to dream. The revelation that interstellar space contains a hidden highway of cosmic debris has forced astronomers to confront an uncomfortable truth about our observational limitations. We've been studying the universe through a keyhole, glimpsing only the brightest and most obvious phenomena, while missing the subtle currents of matter that flow between the stars like invisible rivers carrying the memories of distant worlds. Consider the mathematics of what we're actually detecting. Current surveys can only spot interstellar objects when they come within a few astronomical units of the Sun, when solar heating makes them bright enough to stand out against the background stars. This creates a massive selection bias in our sample of cosmic visitors. We're essentially fishing in a small pond while an entire ocean of interstellar material streams past us undetected. Computer models suggest that for every object like Oumuamua or 2I Borisov that we manage to observe, hundreds or perhaps thousands of similar visitors pass through the outer solar system completely unnoticed. These hidden travelers carry with them the same treasure trove of information about distant stellar systems, but they remain forever beyond the reach of our current instruments. The implications are staggering when you consider the sheer volume of space we're failing to monitor effectively. The gravitational sphere of influence around our Sun extends roughly halfway to the nearest star, creating a detection zone with a radius of over 2 light-years. Within this vast region, interstellar objects are constantly entering, traversing, and departing, most of them invisible to our ground-based telescopes and space-based observatories. This observational challenge has sparked a revolution in detection strategies. Rather than waiting for serendipitous discoveries by existing surveys, astronomers are developing dedicated interstellar object hunting programs. These specialized searches use wide-field telescopes equipped with sensitive cameras that can detect the subtle motion of faint objects against the stellar background. The technical requirements are extraordinary. Unlike asteroids and comets that follow predictable elliptical orbits, interstellar visitors appear as fast-moving dots of light that streak across the sky in straight lines. Distinguishing these genuine interstellar objects from instrumental artifacts, satellite trails, and near-Earth debris requires sophisticated image processing algorithms that can analyze millions of data points in real time. Machine learning systems trained on the subtle signatures of interstellar motion are beginning to show remarkable success in identifying candidate objects within hours of their first detection. These artificial intelligence networks can process telescope data faster than human astronomers, flagging potential interstellar visitors and triggering immediate follow-up observations, while the objects are still bright enough for detailed study. But even with these technological advances, we're still missing the most intriguing category of interstellar objects entirely: the visitors that don't follow the expected patterns, that exhibit behaviors too subtle or too unusual for our automated detection systems to recognize. These anomalous objects might represent the most scientifically valuable discoveries, but they're also the most likely to slip through our observational net. The case of Oumuamua illustrates this challenge perfectly. Its unusual properties only became apparent after weeks of careful observation and analysis. A less thorough follow-up campaign might have classified it as an ordinary asteroid and moved on to other targets. How many similarly anomalous objects have we already missed because they didn't fit our preconceived notions of what interstellar visitors should look like? This question becomes even more troubling when we consider the possibility that some interstellar objects might be artificial in origin. A probe sent by an extraterrestrial civilization would likely be designed to avoid detection, using advanced materials and propulsion systems that produce minimal observable signatures. Such objects might pass through our solar system regularly, without triggering any of our automated detection algorithms. The search for artificial interstellar objects requires a fundamentally different approach than hunting for natural debris. Instead of looking for the thermal signatures and reflected sunlight that characterize rocks and ice, we need to search for the subtle anomalies that might indicate advanced technology. Unusual acceleration patterns, non-thermal radiation sources, or geometric shapes that don't occur in nature. Recent advances in radio astronomy have opened new possibilities for detecting artificial signals from interstellar visitors. The Breakthrough Listen project and similar initiatives now routinely monitor newly discovered interstellar objects for any signs of technological activity. These observations search across a wide range of radio frequencies, looking for the kinds of narrowband signals that might be produced by communication systems or navigation beacons. The sensitivity of these searches is improving rapidly as new radio telescopes come online and digital processing techniques become more sophisticated. We can now detect signals that would have been completely invisible just a decade ago, opening the possibility that previous interstellar visitors might have been transmitting information that we simply lacked the technology to receive. But the most revolutionary development in interstellar object research isn't happening in the realm of detection at all. It's occurring in the laboratories where scientists are learning to decode the chemical messages carried by these cosmic messengers. Advanced mass spectrometry techniques can now identify trace elements and isotopic ratios with unprecedented precision, revealing details about stellar nucleosynthesis and planetary formation processes that occurred around other stars. The chemical signatures preserved in interstellar objects are like fingerprints from alien worlds. The ratio of different oxygen isotopes tells us about the temperature and pressure conditions that existed when the object formed. The abundance of organic molecules reveals information about the carbon chemistry that was occurring in that distant stellar system. Even the microscopic structure of mineral grains can provide clues about the radiation environment and shock processes that shape the object during its formation and subsequent journey through space. These techniques are so sensitive that they can distinguish between objects formed in different regions of the same stellar system. A fragment ejected from the inner asteroid belt of another star would have a distinctly different chemical signature than material that formed in that system's outer comet cloud. By analyzing these subtle differences, we're beginning to piece together detailed maps of the chemical environments that exist around other stars. The data we're collecting is fundamentally changing our understanding of how planetary systems form and evolve. Every stellar system appears to have its own unique chemical fingerprint, shaped by the specific history of stellar evolution, supernova enrichment, and galactic chemical mixing that occurred in that region of space. These differences are subtle but measurable, providing direct evidence for the diversity of planetary formation environments throughout our galaxy. Perhaps most significantly, we're discovering that the chemical signatures of interstellar objects don't always match our theoretical predictions. Some visitors carry isotopic ratios that are difficult to explain using standard models of stellar nucleosynthesis. Others contain organic compounds in combinations that shouldn't be stable under the conditions we believe existed during their formation. These anomalies aren't necessarily evidence of exotic physics or extraterrestrial technology. They might simply reflect gaps in our understanding of stellar evolution and planetary formation processes. But they remind us that the universe is full of surprises, that our theoretical models are still incomplete approximations of reality, rather than perfect descriptions of how nature actually works. The accumulating database of interstellar object properties is beginning to reveal patterns that we never expected. Objects from certain regions of the galaxy appear to have systematically different chemical compositions, suggesting that stellar nucleosynthesis proceeds differently in different galactic environments. Some interstellar visitors carry evidence of exposure to high-energy radiation fields that don't exist in our local stellar neighborhood, hinting at violent processes occurring around other stars. These observations are forcing astronomers to develop new theoretical frameworks for understanding galactic chemical evolution. Rather than viewing stellar systems as isolated islands of matter, we're beginning to recognize them as nodes in a vast network of chemical exchange that operates over billions of years. Matter ejected from one system can travel for eons through interstellar space before being captured by another star's gravitational field, carrying with it the chemical legacy of its original stellar environment. This cosmic recycling program operates with an efficiency that has profound implications for the distribution of heavy elements throughout the galaxy. Elements forged in the cores of massive stars don't just spread through space via supernova explosions and stellar winds. They also travel as passengers aboard interstellar objects, concentrated packages of processed material that can deliver their chemical cargo to stellar systems that might otherwise lack these essential building blocks for planetary formation. The implications for astrobiology are particularly intriguing. If organic molecules can survive the harsh conditions of interstellar space preserved within the protective interiors of comets and asteroids, then these cosmic wanderers might serve as vehicles for distributing the chemical precursors of life throughout the galaxy. A single impact event could deliver not just water and carbon compounds to a young planet, but entire libraries of complex organic chemistry that evolved under alien skies. This possibility transforms our understanding of how life might arise and spread throughout the universe. Rather than requiring independent genesis events in each stellar system, biological evolution could be a galactic phenomenon, with the fundamental building blocks of life traveling between stars as passengers aboard interstellar debris. The chemical signatures we detect in these cosmic messengers might include evidence of biological processes that occurred billions of years ago around stars we'll never be able to visit directly. The search for such biosignatures has become one of the most exciting frontiers in astrobiology. Researchers are developing increasingly sophisticated techniques for identifying the subtle chemical imbalances that biological processes create in their environment. The presence of certain organic compounds in specific ratios, or the detection of isotopic fractionation patterns that match those produced by living organisms, could provide the first direct evidence that life exists elsewhere in the galaxy. But detecting these signatures requires pushing analytical chemistry to its absolute limits. The amounts of material available for study are minuscule, often just microscopic grains embedded within larger rocky or icy matrices. Extracting meaningful chemical information from such tiny samples demands techniques borrowed from forensic science, nuclear physics, and materials engineering. The instruments being developed for this purpose are marvels of modern technology. Ion beam microscopes can map the chemical composition of individual mineral grains with nanometer scale resolution. Mass spectrometers sensitive enough to detect single atoms can measure isotopic ratios in samples weighing less than a picogram. Laser ablation systems can vaporize microscopic regions of interstellar material for analysis without disturbing the surrounding matrix. These techniques are revealing levels of chemical complexity in interstellar objects that were unimaginable just a few years ago. Rather than the simple mixtures of rock and ice that early models predicted, we're discovering that these cosmic messengers carry within them detailed records of stellar evolution, planetary formation, and potentially even biological activity that occurred around other stars. The chemical diversity is staggering. Some interstellar objects contain minerals that can only form under extreme pressure conditions, suggesting they originated in the cores of differentiated planetoids that were subsequently disrupted by violent impacts. Others carry isotopic signatures indicating formation in the vicinity of particular types of stars, allowing us to trace their origins back to specific stellar populations within our galaxy. Most intriguingly, we're beginning to find chemical signatures that don't match any known natural processes, unusual isotopic ratios, unexpected molecular combinations, and trace element abundances that fall outside the ranges predicted by stellar nucleosynthesis models. These anomalies might represent previously unknown astrophysical processes, or they could indicate something even more extraordinary: the possibility that some of these chemical anomalies might have artificial origins is being taken seriously by researchers around the world. Advanced civilizations capable of interstellar travel would likely have developed materials, science technologies far beyond our current capabilities. The chemical signatures of such technologies might be detectable in the composition of artificial objects passing through our solar system, even if we lack the context to understand what we're observing. This prospect has added a new dimension to the chemical analysis of interstellar objects. In addition to searching for evidence of natural astrophysical processes and potential biosignatures, researchers are now looking for any indication of deliberate chemical modification or technological processing. The discovery of materials with properties that can't be explained by natural formation processes would represent one of the most significant scientific discoveries in human history. But even setting aside the possibility of artificial objects, the natural chemical diversity revealed by interstellar visitors is revolutionizing our understanding of planetary formation and stellar evolution. Each new detection adds another data point to our growing map of galactic chemical geography, revealing the complex interplay of processes that have shaped the distribution of elements throughout our cosmic neighborhood. The patterns emerging from this data are beginning to tell a coherent story about how matter flows through the galaxy over cosmic timescales. Stars form from chemically enriched gas clouds that contain the processed remnants of previous stellar generations. Planetary systems assemble from this pre-enriched material, incorporating the chemical legacy of billions of years of stellar evolution. Some of this material is subsequently ejected into interstellar space, carrying with it detailed records of the conditions that existed during planetary formation. These ejected fragments then embark on journeys that can last for millions or billions of years, traveling vast distances through the galaxy before potentially being incorporated into new stellar systems. The chemical information they carry provides direct evidence about the diversity of planetary formation environments that exist throughout our galactic neighborhood. Data that would be impossible to obtain through remote observation alone. This cosmic recycling program operates on scales and timescales that dwarf any earthly recycling process. Material ejected from stellar systems billions of years ago is still traveling through interstellar space, carrying within it the chemical fingerprints of worlds that may no longer exist. Meanwhile, fragments of our own solar system, launched into space during the chaotic early phases of planetary formation, are presumably carrying Earth's chemical signature to distant stellar neighborhoods, where they might one day be incorporated into alien worlds. The implications of this material exchange are profound and far-reaching. Rather than viewing stellar systems as isolated entities that evolve independently, we must recognize them as participants in a vast galactic ecosystem where chemical information flows freely between distant worlds. The elements that make up our planet, the molecules that form our bodies, the very atoms that enable our consciousness to exist, all carry within them the chemical legacy of countless stellar generations and the processed remnants of worlds that formed around other stars. This perspective transforms our understanding of our place in the cosmic order. We're not inhabitants of an isolated planetary system orbiting an unremarkable star. We're participants in a galactic community that has been exchanging matter, energy, and chemical information for billions of years. The interstellar objects that pass through our solar system are messengers from this broader community, carrying news from distant worlds and bringing us samples of the chemical diversity that exists throughout our galaxy. The recognition that we're part of this larger galactic ecosystem has profound implications for how we think about the search for life in the universe. Rather than focusing solely on potentially habitable exoplanets orbiting distant stars, we must also consider the possibility that evidence of extraterrestrial life might literally be delivered to our doorstep aboard interstellar visitors. The chemical signatures of biological processes that occurred billions of years ago around other stars could be preserved within the protective matrices of cosmic debris, waiting for our increasingly sophisticated analytical techniques to decode their messages. This possibility has transformed astrobiology from a largely theoretical discipline into an active experimental science. Rather than relying solely on remote sensing and computer models to understand the potential for life around other stars, we can now conduct direct chemical analysis of material from those stellar systems. Every new interstellar object detection represents an opportunity to search for biosignatures that might reveal the existence of life elsewhere in the galaxy. The techniques required for this search are pushing the boundaries of analytical chemistry and materials science. Detecting the subtle chemical imbalances that biological processes create requires instruments capable of measuring isotopic ratios and molecular abundances with unprecedented precision. The samples available for analysis are often microscopic, demanding techniques borrowed from nanotechnology and quantum sensing to extract meaningful information from minuscule amounts of material. But the potential rewards justify these extraordinary technical challenges. The discovery of genuine biosignatures in interstellar material would represent confirmation that life exists elsewhere in the galaxy, that the chemical processes responsible for biological evolution have operated around other stars. Such a discovery would fundamentally transform our understanding of life's place in the universe, revealing that the emergence of biological complexity is not a unique accident confined to Earth, but a natural consequence of cosmic chemical evolution. The search for these biosignatures is complicated by the fact that we don't yet fully understand how biological processes might be preserved over the billions of years that interstellar objects spend traveling through space. The harsh radiation environment, extreme temperature fluctuations, and chemical interactions with cosmic rays could potentially erase or modify the subtle signatures that biological activity creates in its environment. Yet recent research suggests that certain types of biosignatures might be remarkably stable over cosmic timescales. The isotopic fractionation patterns that biological processes create, the specific ratios of organic molecules that living systems produce, and even the microscopic structures that some organisms leave behind could potentially survive the journey between star systems. The key is identifying which signatures are most likely to be preserved and developing techniques sensitive enough to detect them in the tiny samples available for analysis. This research is revealing unexpected connections between disciplines that were previously considered completely separate. Understanding how biosignatures might be preserved in interstellar objects requires expertise in biochemistry, materials science, radiation physics, and space weathering processes. The interdisciplinary nature of this work is producing insights that wouldn't be possible within the traditional boundaries of academic specialization. The implications extend far beyond the search for extraterrestrial life. The chemical processes that create and preserve biosignatures are fundamentally similar to those involved in prebiotic chemistry and the emergence of life from non-living matter. By studying how organic molecules behave under the extreme conditions of interstellar space, we're gaining new insights into the chemical pathways that might have led to the origin of life on Earth and potentially on other worlds. These insights are feeding back into our understanding of planetary habitability and the conditions necessary for life to emerge and evolve. Rather than viewing habitability as a simple function of temperature, pressure, and chemical composition, we're beginning to recognize it as a complex phenomenon that depends on the entire history of chemical evolution within a given stellar system. The organic molecules delivered by interstellar objects, the trace elements incorporated during planetary formation, and the ongoing chemical exchange with the broader galactic environment all play roles in determining whether a world can support the emergence and evolution of life. This more sophisticated understanding of habitability is influencing how we prioritize targets for future exoplanet missions and direct imaging campaigns. Rather than focusing solely on Earth-sized planets in the habitable zones of sun-like stars, we're beginning to consider the broader chemical context in which planetary systems form and evolve. Stellar systems with unusual chemical compositions, evidence of recent material exchange with the interstellar medium, or signatures of organic chemistry in their circumstellar environments might represent particularly promising targets for the search for life. The growing database of interstellar object properties is providing crucial calibration data for these assessments. By measuring the chemical diversity that actually exists in our galactic neighborhood, rather than relying on theoretical predictions alone, we can develop more realistic models of planetary formation and chemical evolution. This empirical approach is revealing that the galaxy contains far more chemical diversity than our models predicted, suggesting that the range of potentially habitable environments might be correspondingly broader. But perhaps the most significant implication of interstellar object research is how it's changing our perception of time and scale in cosmic evolution. The objects we're studying today carry within them chemical information that spans the entire history of our galaxy. Isotopic ratios forged in the cores of the first generation of massive stars, organic molecules synthesized in the cold molecular clouds where new stars are born, and potentially even biosignatures from worlds that flourished billions of years ago are all preserved within these cosmic time capsules. This deep time perspective reveals the universe as a far more dynamic and interconnected system than we previously imagined. Chemical information flows between stellar systems over billions of years, creating a kind of galactic memory that preserves evidence of processes and events that occurred throughout cosmic history. The interstellar objects passing through our solar system today are messengers from this deep past, carrying news from epochs and locations that we could never hope to study directly. The recognition that we have access to this cosmic archive has profound implications for how we approach fundamental questions about the universe and our place within it. Rather than being limited to studying the local conditions that exist in our immediate stellar neighborhood, we can potentially trace the chemical evolution of matter back through billions of years of galactic history. The answers to questions about stellar nucleosynthesis, planetary formation, and the emergence of life might be encoded in the chemical signatures of interstellar debris that we can collect and analyze in our laboratories. This transformation from passive observers of distant phenomena to active archaeologists of cosmic history represents one of the most significant paradigm shifts in astronomy since the development of spectroscopy. We're no longer limited to inferring the properties of distant objects from their electromagnetic radiation. We can now conduct hands-on analysis of material from throughout our galaxy, studying the actual atoms and molecules that participated in stellar evolution and planetary formation processes around other stars. The psychological impact of this transformation is difficult to overstate. holding a fragment of material that formed around another star, knowing that it carries within its crystal structure the chemical memory of processes that occurred billions of years ago in a completely different stellar environment, connects us to the broader galaxy in ways that no amount of theoretical knowledge could match. These aren't abstract concepts from textbooks, but tangible evidence of our participation in a cosmic community that spans space and time on scales that dwarf human comprehension. Yet for all the revolutionary insights that interstellar objects have provided, we're still in the earlier stages of this new field of research. The objects we've studied so far represent a tiny and potentially biased sample of the material that flows between stellar systems. Future detections will likely reveal even greater diversity in chemical composition, physical properties, and potentially even evidence of processes we haven't yet imagined. The next interstellar visitor could fundamentally change our understanding of galactic evolution, planetary formation, or the prevalence of life in the universe. It might carry chemical signatures that revolutionize our models of stellar nucleosynthesis, or isotopic ratios that reveal previously unknown astrophysical processes. Most intriguingly, it might exhibit properties that can only be explained by invoking artificial origins, providing the first direct evidence that we're not alone in the galaxy. As we stand on the threshold of this new era of cosmic archaeology, we find ourselves confronting questions that seemed purely academic just a few years ago. The universe is revealing itself to be far more interconnected, dynamic, and potentially inhabited than we ever dared imagine. The interstellar objects streaming through our solar system are messengers from this broader cosmic community, carrying within them the keys to understanding our place in a galaxy that is alive with the flow of matter, energy, and potentially life itself between distant worlds. The detection capabilities we're developing for interstellar objects represent a fascinating convergence of cutting-edge technology and fundamental physics. As our instruments become more sensitive and our analysis techniques more sophisticated, we're beginning to glimpse the true scale and complexity of the material highways that connect stellar systems across our galaxy. Consider the engineering marvel that modern sky surveys represent. The Catalina Sky Survey operates multiple telescopes simultaneously, scanning vast swaths of sky each night with cameras sensitive enough to detect objects millions of times fainter than what the human eye can perceive. Their automated systems process terabytes of data in real time, comparing each new image against a database of known objects to identify anything that moves with the characteristic signature of an interstellar visitor. The computational challenges are staggering. Every night, these surveys generate millions of measurements of stellar positions, brightness variations, and orbital trajectories. Sophisticated algorithms must sift through this avalanche of data, distinguishing genuine interstellar objects from instrumental artifacts, satellite streaks, and the much more numerous population of asteroids and comets that belong to our own solar system. Machine learning systems trained on the subtle patterns of interstellar motion have become remarkably adept at identifying candidate objects within hours of their first detection. These artificial intelligence networks can recognize the telltale signatures of hyperbolic trajectories even when the observational arc spans only a few hours, triggering immediate alerts to observatories around the world. But perhaps the most intriguing aspect of current detection efforts is what they're revealing about the objects we're missing. Statistical analysis of our confirmed detections suggests that we're only seeing a tiny fraction of the interstellar visitors that actually pass through our solar system. For every object like Oumuamua or 2I Borisov that becomes bright enough for detailed study, dozens or perhaps hundreds of similar objects presumably traverse the outer solar system undetected. This observational selection effect creates profound biases in our understanding of interstellar object populations. We're preferentially detecting objects that pass close to the Sun, where solar heating makes them bright enough to stand out against the stellar background. Objects that follow trajectories through the outer solar system, or those composed of materials that don't reflect sunlight efficiently, remain invisible to our current generation of instruments. The implications are particularly significant when we consider the possibility that some interstellar objects might be artificial in origin. A probe designed by an advanced civilization would likely be engineered to minimize its observational signatures, using materials and propulsion systems that produce minimal thermal emission or reflected light. Such objects might routinely pass through our solar system without triggering any of our automated detection algorithms. This possibility has sparked the development of entirely new search strategies specifically designed to identify anomalous objects that don't fit the expected patterns of natural space debris. Radio telescopes now routinely monitor newly discovered interstellar objects for any signs of artificial signals or technological activity. Advanced imaging systems search for geometric shapes or surface features that might indicate manufactured rather than natural origins. The technical specifications required for these searches push the boundaries of what's possible with current technology. Detecting a narrowband radio signal from an object the size of Oumuamua requires sensitivity levels that would have been unimaginable just a decade ago. The signal processing algorithms must account for Doppler shifts caused by the object's rapid motion, frequency drifts from potential rotation or tumbling, and interference from terrestrial radio sources. Yet even more challenging is the question of what we should be looking for. An artificial object created by an extraterrestrial civilization might operate according to principles we don't understand, using technologies that produce signatures we haven't learned to recognize. The absence of obvious artificial signals doesn't necessarily indicate that an object is natural in origin. It might simply mean that we lack the conceptual framework to interpret what we're observing. This uncertainty has led to a more nuanced approach to interstellar object classification. Rather than attempting to definitively categorize objects as natural or artificial, researchers are developing statistical frameworks that assign probabilities to different explanations based on the available evidence. An object with unusual properties might receive a higher probability of artificial origin without being definitively classified as such. The case of Oumuamua illustrates both the power and limitations of this approach. Its extreme elongation, mysterious acceleration, and apparent lack of outgassing created a probability distribution that included both exotic natural explanations and the possibility of artificial origin. Years of analysis and debate have refined these probabilities, but haven't eliminated any of the proposed explanations entirely. This ambiguity reflects a deeper challenge in the search for evidence of extraterrestrial intelligence. We're attempting to recognize signs of technology that might be based on physical principles we haven't discovered, created by intelligences that think in ways we can't anticipate, and designed for purposes we can't imagine. The challenge isn't just technical, but fundamentally epistemological. How do you recognize intelligence when it operates according to rules you don't understand? How do you distinguish advanced technology from natural phenomena when both might produce effects that seem impossible according to your current theoretical framework? These questions push us toward the limits of scientific methodology itself, forcing us to confront the assumptions that underlie our approach to understanding the universe. The development of more sensitive detection systems is providing partial answers to some of these questions, while raising entirely new ones. Next-generation space telescopes operating in the infrared will be able to detect the thermal signatures of interstellar objects at much greater distances than is currently possible. This expanded detection range will provide longer observation windows and larger statistical samples for analysis. Ground-based facilities are also evolving rapidly. The upcoming Vera C. Rubin Observatory will survey the entire visible sky every few nights with unprecedented sensitivity and precision. Its massive camera system will generate more astronomical data than all previous sky surveys combined, likely increasing the detection rate of interstellar objects by orders of magnitude. But perhaps the most revolutionary development is occurring in the realm of rapid response space missions. Concepts for intercepting interstellar objects are advancing from theoretical studies to serious engineering proposals. These missions would use advanced propulsion systems to match the hyperbolic trajectories of interstellar visitors, enabling close-up study of material from other star systems. The engineering challenges are formidable. Interstellar objects often follow poorly determined trajectories until they're already past their closest approach to the Sun. Mission planners would have only weeks or months to design flight paths, prepare scientific instruments, and launch spacecraft capable of rendezvousing with targets moving at tens of kilometers per second. Solar sail technology offers one promising solution to this challenge. Large, ultra-thin sails could accelerate spacecraft to the high velocities needed for interstellar object rendezvous, without requiring massive amounts of fuel. Ion propulsion systems provide another option, offering high specific impulse that enables efficient acceleration over extended periods. The scientific instruments required for such missions must be designed to operate under conditions unlike anything encountered in previous space missions. They would need to function reliably after years of interstellar cruise, withstand the thermal shock of rapid deceleration, and collect meaningful data during brief high-speed encounters with targets of unknown composition and structure. Advanced imaging systems would need to resolve surface features and internal structure during flybys lasting only hours or minutes. Mass spectrometers would analyze samples of gas, dust, and potentially solid material ejected from the object's surface. Radio and plasma wave instruments would search for any signs of artificial signals or unusual electromagnetic activity. The data collected during such encounters could revolutionize our understanding of interstellar objects and their role in galactic evolution. Direct sampling of material from other stellar systems would provide unprecedented insights into the chemical processes that occur during planetary formation around different types of stars. Detailed images of interstellar object surfaces and internal structures would reveal information about formation mechanisms, space weathering processes, and the physical conditions that exist in interstellar space. But perhaps most significantly, a successful rendezvous mission could provide definitive answers to questions about the artificial or natural origin of anomalous interstellar objects. Close-up inspection would reveal surface textures, material properties, and structural details that could distinguish between natural formation and technological manufacture. The possibility of discovering clear evidence of extraterrestrial technology through such a mission has profound implications that extend far beyond astronomy and space science. It would represent confirmation that intelligence and technology have evolved elsewhere in the galaxy, that we're not alone in our capacity to understand and manipulate the physical world. Yet even this momentous discovery would raise as many questions as it answered. The detection of artificial objects in interstellar space would tell us that technological civilizations exist, but it wouldn't necessarily provide information about their current status, location, or intentions. An interstellar probe might represent a civilization that flourished billions of years ago, or one that continues to operate in regions of the galaxy we can't observe directly. The objects themselves might be designed for purposes we can't comprehend, operating according to mission parameters that reflect values and priorities entirely different from our own. They might be scientific instruments conducting long-term surveys of stellar evolution, communication relays maintaining contact between distant outposts, or automated systems with functions we lack the conceptual framework to understand. This uncertainty about purpose and origin would create new challenges for humanity's response to such discoveries. How do you interact with technology that you don't understand, created by intelligences that might think in fundamentally different ways? How do you determine whether such objects represent opportunities for communication or potential threats to human civilization? These questions push us toward consideration of protocols and frameworks for responding to evidence of extraterrestrial intelligence. The scientific community has begun developing guidelines for handling such discoveries, but the complexity of potential scenarios makes it difficult to prepare for all contingencies. The detection of artificial interstellar objects would also have profound implications for our understanding of the prevalence and distribution of intelligence in the galaxy. If such objects are common enough to be detected by our surveys, it would suggest that technological civilizations are relatively abundant and that interstellar travel or communication is a natural development in the evolution of intelligence. Conversely, if artificial objects prove to be extremely rare, it might indicate that the emergence of technological intelligence is an unlikely event, or that civilizations capable of interstellar activities tend to be short-lived. The statistical properties of interstellar object populations could provide crucial data for resolving questions about the frequency and longevity of technological civilizations throughout the galaxy. But even setting aside the possibility of artificial objects, the natural interstellar visitors we're discovering are revolutionizing our understanding of galactic evolution and planetary formation processes. Each new detection adds another data point to our growing map of chemical diversity throughout our stellar neighborhood. The patterns emerging from this data are beginning to reveal the complex history of matter circulation between stellar systems. Objects ejected during the violent early phases of planetary formation carry with them detailed records of the conditions that existed in their birth systems. By analyzing these chemical signatures, we can reconstruct the nucleosynthetic history of different regions of the galaxy and trace the flow of processed materials between stellar generations. This cosmic archaeology is revealing a galaxy that is far more dynamic and interconnected than we previously imagined. Rather than evolving in isolation, stellar systems participate in a vast network of chemical exchange that operates over billions of years. Material ejected from one system can travel for eons through interstellar space before being incorporated into newly forming planetary systems, carrying with it the chemical legacy of its origins. The implications for understanding planetary habitability are particularly significant. The heavy elements necessary for rocky planet formation and the organic molecules that serve as precursors to biological chemistry are distributed throughout the galaxy through this interstellar transport system. Stellar systems that might otherwise lack these essential ingredients for habitability can receive them through the capture of chemically enriched interstellar debris. This process might explain some of the puzzling observations we're making about exoplanet compositions and the apparent ubiquity of potentially habitable worlds throughout the galaxy. Rather than requiring each stellar system to generate all the necessary ingredients for habitability through local processes, planets can inherit chemical complexity from materials that originated in completely different stellar environments. The recognition that interstellar objects serve as vehicles for transporting chemical complexity throughout the galaxy has also transformed our thinking about the potential for life to spread between stellar systems. If microorganisms can survive the harsh conditions of interstellar space preserved within the protective interiors of comets and asteroids, then these cosmic wanderers might serve as arcs for distributing life throughout our galactic neighborhood. Recent laboratory studies suggest that certain extremophile organisms might indeed be capable of surviving the radiation exposure temperature fluctuations, and chemical stresses associated with interstellar travel. Spores and other dormant life forms could potentially remain viable for millions or even billions of years, while embedded within the matrices of interstellar objects. This possibility adds a biological dimension to the chemical exchange network that connects stellar systems throughout the galaxy. Rather than just transporting inorganic materials and organic precursors, interstellar objects might also serve as vehicles for the actual transfer of living organisms between worlds. A single impact event could potentially seed an entire planet with genetic material that evolved under completely different stellar conditions. The implications for astrobiology are profound and deeply unsettling. If life can indeed travel between stellar systems aboard interstellar debris, then the emergence of biological complexity might not require independent genesis events in each stellar system. Instead, life could be a galactic phenomenon, spreading from world to world through the natural processes of gravitational dynamics and impact geology. This perspective transforms the search for extraterrestrial life from a question about the probability of independent origins to an investigation of how biological information flows through the galaxy over cosmic timescales. Rather than asking whether life arose independently on other worlds, we might need to ask whether the life we observe on Earth represents a unique evolutionary experiment or one branch of a much larger biological network that spans multiple stellar systems. The chemical signatures we're detecting in interstellar objects are beginning to provide clues about these possibilities. Some visitors carry isotopic ratios and organic molecule abundances that are difficult to explain through purely abiotic processes. While these signatures don't constitute definitive evidence of biological origin, they suggest that the chemistry of interstellar objects might be more complex and potentially more biological than we initially assumed. Advanced analytical techniques are being developed specifically to search for these subtle biosignatures in interstellar material. Mass spectrometry systems capable of detecting individual organic molecules, isotope ratio measurements with unprecedented precision, and techniques for identifying the microscopic structures that biological processes create are all being applied to samples of interstellar debris. The challenges are immense. The amounts of material available for analysis are often microscopic, requiring techniques borrowed from forensic science and materials engineering to extract meaningful chemical information. The signatures of biological activity might be subtle and easily confused with the products of abiotic chemistry or space weathering processes. Yet the potential rewards justify these extraordinary technical challenges. The discovery of genuine biosignatures in interstellar material would represent the first direct evidence that biological processes have occurred elsewhere in the galaxy. Such a discovery would fundamentally transform our understanding of life's place in the universe, revealing that the emergence of biological complexity is not unique to Earth, but a natural consequence of cosmic chemical evolution. The implications would extend far beyond astrobiology itself. The recognition that life might be a galactic phenomenon would influence how we approach questions about planetary protection, the ethics of space exploration, and our responsibilities as a potentially spacefaring species. If life routinely travels between stellar systems, then our expansion into space might involve encounters with biological systems that evolved under alien conditions, but share common origins with terrestrial life. These considerations are already influencing mission planning for future interstellar object encounters. Protocols are being developed for handling potentially biologically contaminated samples, sterilization procedures for spacecraft instruments, and containment systems for materials that might harbor viable microorganisms. The technical requirements for such missions push the boundaries of current engineering capabilities. Spacecraft must be designed to collect samples without contaminating them with terrestrial microorganisms, store potentially viable biological material under appropriate conditions, and return samples to Earth for analysis in high-containment laboratory facilities. But perhaps the most challenging aspect of searching for life in interstellar objects is developing the conceptual frameworks necessary to recognize biological signatures that might be fundamentally different from anything we've encountered on Earth. Life that evolved under different stellar conditions, in different chemical environments, might produce metabolic byproducts and structural features that don't match our terrestrial-based expectations. This challenge requires a more general approach to recognizing the signatures of biological activity, one that focuses on the fundamental thermodynamic and informational properties that all living systems must possess, rather than the specific chemical pathways that terrestrial life happens to use. Such an approach might reveal forms of biological organization that we haven't yet imagined, expanding our understanding of what life can be and how it might manifest in different cosmic environments. The search for these exotic forms of biological activity is pushing the boundaries of multiple scientific disciplines simultaneously. Understanding how life might survive and evolve during interstellar travel requires expertise in radiation biology, extremophile physiology, and space weathering processes. Recognizing the signatures such life might leave behind demands advances in analytical chemistry, materials science, and information theory. This interdisciplinary approach is producing insights that wouldn't be possible within the traditional boundaries of academic specialization. The intersection of astrobiology with materials science is revealing new understanding about how biological information can be preserved in mineral matrices over cosmic timescales. The merger of radiation physics with evolutionary biology is providing insights into how life might adapt to the extreme environments of interstellar space. These insights are feeding back into our understanding of terrestrial life and its evolutionary history. The processes that might allow life to survive interstellar travel are similar to those that enable organisms to survive other extreme environments on Earth. By studying how life might adapt to cosmic conditions, we're gaining new perspectives on the limits and possibilities of biological organization in general. The implications extend beyond biology to questions about the nature of information and complexity in the universe. If biological systems can indeed survive and potentially evolve during interstellar travel, then they represent a mechanism for transporting not just chemical complexity, but informational complexity between stellar systems. The genetic codes and metabolic pathways that evolve around one star could potentially influence biological evolution around completely different stars. This possibility suggests that the universe might contain networks of information flow that operate on scales and timeframes far beyond anything we've previously considered. Rather than viewing biological evolution as a planetary phenomenon, we might need to think about it as a galactic process that connects the evolutionary histories of worlds separated by vast distances and eons of time. The recognition that such networks might exist is transforming how we think about intelligence and consciousness in the universe. If information can flow between stellar systems through biological mechanisms, then the emergence of intelligence around one star might influence the development of intelligence around other stars through pathways we're only beginning to understand. These considerations are pushing us toward a more sophisticated understanding of our place in the cosmic order. Rather than viewing Earth as an isolated experiment in biological evolution, we might be participants in a much larger process of cosmic evolution toward complexity and consciousness. The interstellar objects streaming through our solar system might be messengers from this broader evolutionary network, carrying within them information about the pathways through which matter organizes itself into increasingly complex and potentially conscious forms. The questions this possibility raises are both profound and deeply unsettling. If consciousness is indeed part of a larger cosmic evolutionary process, then what role does human intelligence play in this grand scheme? Are we simply one more step in a progression toward greater complexity, or do we represent something fundamentally new in the universe's exploration of its own possibilities? The answers to these questions might be encoded in the chemical signatures and physical properties of the interstellar visitors that continue to arrive in our solar system. Each new detection represents an opportunity to probe deeper into the mystery of cosmic evolution and our place within it. The next interstellar object might carry with it evidence that transforms our understanding of life, intelligence, and consciousness in the universe. As we continue to develop more sophisticated techniques for detecting and analyzing these cosmic messengers, we find ourselves standing at the threshold of discoveries that could fundamentally alter humanity's understanding of its place in the universe. The revelation that we're not alone, that intelligence and complexity emerge naturally from cosmic evolutionary processes, would represent a transformation in human consciousness comparable to the Copernican revolution or the discovery of deep time. Yet even as we prepare for such revelations, we must also consider the possibility that the universe might be far stranger and more complex than our current theories suggest. The interstellar objects we're studying might represent phenomena that transcend our current understanding of physics, chemistry, and biology. They might be messengers from realms of reality that we haven't yet learned to perceive or comprehend. This uncertainty about the true nature of reality brings us to one of the most unsettling aspects of our growing catalogue of interstellar visitors. The more we learn about these objects, the more we realise how much we don't understand about the fundamental processes that govern matter and energy in the universe. Each new detection challenges our assumptions about what's possible, what's natural, and what should exist in the space between stars. Consider the implications of discovering that some interstellar objects exhibit properties that can't be explained by our current understanding of physics. Such discoveries wouldn't just represent gaps in our knowledge. They would suggest that reality operates according to principles we haven't yet recognized, that the universe contains phenomena that transcend our theoretical frameworks entirely. The possibility is both thrilling and deeply unsettling. Throughout human history, our greatest scientific breakthroughs have come from recognizing that nature operates in ways we never expected. The quantum mechanical behavior of matter, the relativistic nature of space and time, the expansion of the universe itself, all emerged from observations that seemed impossible according to the prevailing theories of their time. Could interstellar objects be delivering similar revelations about the nature of reality? Might these cosmic wanderers carry within them evidence of physical processes that we haven't yet learned to recognize or understand? The answer may determine whether our current scientific worldview represents genuine insight into the cosmos, or merely the latest chapter in humanity's ongoing struggle to comprehend a universe that perpetually exceeds our expectations. The chemical analysis techniques we're developing to study these visitors are revealing levels of complexity that our models never predicted. Rather than the simple mixtures of rock, ice, and organic molecules that early theories suggested, we're finding intricate structures that seem to preserve detailed records of processes we can barely imagine. Mineral grains that appear to have formed under impossible conditions, isotopic ratios that don't match any known nucleosynthetic pathways, and molecular arrangements that challenge our understanding of how chemistry works in extreme environments. Some of these anomalies might represent previously unknown astrophysical processes. The interiors of forming planetary systems might harbor conditions and chemical reactions that we've never encountered in terrestrial or laboratory environments. The long journey through interstellar space might expose materials to radiation fields, magnetic environments, and temperature cycles that create chemical modifications we haven't learned to predict. But other anomalies are more difficult to dismiss as mere gaps in our astrophysical knowledge. Structures that seem too organized to result from random processes, chemical signatures that suggest deliberate modification or processing, and physical properties that appear to violate fundamental principles of material science. These observations push us toward uncomfortable questions about the nature of the objects we're studying. The possibility that some interstellar visitors might represent technology rather than natural debris has evolved from speculative hypothesis to serious scientific consideration. Advanced civilizations capable of interstellar travel would likely have developed materials science capabilities far beyond our current understanding. The artifacts of such civilizations might exhibit properties that seem impossible according to our current theories, not because they violate physical laws, but because they exploit aspects of physics we haven't yet discovered. This prospect has profound implications for how we interpret anomalous observations. A chemical signature that seems to violate our understanding of stellar nucleosynthesis might actually represent evidence of industrial processes operating on cosmic scales, physical properties that appear to defy our models of materials. Science might reflect technologies based on principles we haven't yet learned to recognize. The challenge lies in distinguishing between genuine technological artifacts and natural phenomena that simply exceed our current understanding. Both categories might produce observations that seem impossible according to our existing theories. Both might challenge our fundamental assumptions about how the universe works and what kinds of processes are possible in cosmic environments. The development of criteria for making these distinctions has become one of the most sophisticated challenges in modern astronomy. Researchers are developing statistical frameworks that can assess the probability that a given set of observations represents artificial rather than natural origins. These frameworks must account for the possibility that our theoretical understanding is incomplete, while still providing meaningful guidance for interpreting anomalous data. The complexity of this task reflects a deeper challenge in the search for evidence of extraterrestrial intelligence. We're attempting to recognize signs of technology that might be based on scientific principles we haven't discovered, created by intelligences that approach problem solving in ways we can't anticipate, and designed for purposes that might be incomprehensible to us. How do you distinguish between advanced technology and exotic natural phenomena when both might produce effects that transcend your current understanding? How do you recognize intelligence when it operates according to rules you haven't learned to perceive? These questions push us toward the fundamental limits of scientific methodology and force us to confront the assumptions that underlie our approach to understanding the universe. The statistical analysis of interstellar object properties is beginning to reveal patterns that we never expected to find. Objects from certain regions of the galaxy appear to have systematically different characteristics, suggesting that the processes responsible for their formation and ejection vary significantly across different stellar environments. Some regions seem to produce objects with unusual chemical compositions, while others generate debris with anomalous physical properties. These patterns might reflect genuine differences in stellar evolution and planetary formation processes throughout the galaxy. Different metallicity environments, varying supernova rates, and diverse stellar population mixes could create systematic variations in the types of objects ejected from different galactic regions. Such variations would provide crucial insights into how galactic evolution proceeds on the largest scales. But some of the patterns we're observing are more difficult to explain through natural astrophysical processes alone. Certain types of anomalous objects seem to originate preferentially from specific directions in the galaxy, suggesting either unknown selection effects in our detection methods or genuine asymmetries in the distribution of whatever processes create these unusual visitors. The possibility that technological civilizations might be responsible for some of these patterns adds another layer of complexity to the interpretation. If advanced societies are indeed launching objects into interstellar space, whether for exploration, communication, or purposes we can't imagine, then the statistical properties of interstellar object populations might reflect the geography of intelligence throughout our galactic neighborhood. Such patterns could provide the first indirect evidence of large-scale technological activity operating on galactic scales. The distribution of artificial objects throughout interstellar space might reveal information about the prevalence, locations, and activities of civilizations we can't detect through any other means. The implications are staggering when you consider the temporal scales involved. Objects launched into interstellar space millions or billions of years ago are still traveling between stellar systems, carrying with them evidence of civilizations that might have flourished and vanished long before Earth even formed. The interstellar debris field might preserve archaeological evidence of technological societies spanning the entire history of our galaxy. This perspective transforms the study of interstellar objects from a branch of astronomy into a form of galactic archaeology. Rather than simply investigating natural astrophysical processes, we might be excavating the technological remains of civilizations that explored the galaxy eons before humanity emerged. The chemical signatures we detect, the physical properties we measure, and the trajectory patterns we observe might all contain information about species and societies we could never encounter directly. The techniques required for this kind of archaeological investigation push the boundaries of multiple scientific disciplines simultaneously. Recognizing the signatures of ancient technology requires understanding not just materials science and engineering, but also the evolutionary pathways through which intelligence might develop, and the kinds of goals that technological civilizations might pursue over cosmic timescales. This interdisciplinary approach is producing insights that wouldn't be possible within traditional academic boundaries. The intersection of archaeology with astrobiology is revealing new understanding about how information and technology might be preserved over geological time periods. The merger of materials science with evolutionary biology is providing perspectives on how intelligence might manipulate matter and energy in ways we haven't yet imagined. These insights are feeding back into our understanding of terrestrial civilization and its long-term prospects. The processes that might allow technological artifacts to survive interstellar travel are similar to those that determine how human civilization might preserve its legacy over cosmic time scales. By studying how intelligence might manifest itself in interstellar space, we're gaining new perspectives on the challenges and opportunities that face any technological species. The implications extend beyond technology to questions about the nature of intelligence and consciousness in the universe. If technological artifacts can indeed survive and potentially function during interstellar travel, then they represent a mechanism for extending the influence of intelligence far beyond the biological lifespans of their creators. The ideas and intentions that motivate the construction of such objects could potentially influence cosmic evolution long after their originating civilizations have disappeared. This possibility suggests that intelligence might play a more significant role in cosmic evolution than we've previously recognized. Rather than being a rare and temporary phenomenon confined to the surfaces of a few rocky planets, intelligence might be a persistent feature of galactic ecology, influencing the flow of matter and energy between stellar systems through technological mechanisms we're only beginning to understand. The recognition that such mechanisms might exist is transforming how we think about humanity's place in the cosmic order. Rather than viewing ourselves as isolated observers of an indifferent universe, we might be participants in a much larger community of intelligence that spans both space and time. The interstellar objects streaming through our solar system might be messages from this community, carrying within them information about the pathways through which intelligence explores and shapes its cosmic environment. What's particularly intriguing about this possibility is how it might resolve some of the paradoxes that have long puzzled researchers studying the prevalence of intelligence in the universe. If technological civilizations typically have short lifespans compared to cosmic timescales, how can they have any significant influence on galactic evolution? But if intelligence can extend its reach through self-replicating or long-lived technological systems, then even brief episodes of biological intelligence might leave lasting impacts on cosmic development. The interstellar objects we're discovering might represent evidence of such impacts. Rather than being mere debris from planetary formation processes, some of these visitors might be the fossilized remains of technological ecosystems that operated on scales we can barely comprehend. The chemical modifications we detect, the structural anomalies we observe, and the trajectory patterns we measure might all preserve information about how intelligence has shaped the flow of matter through our galactic neighborhood. This perspective raises profound questions about the nature of cosmic evolution and our role within it. If intelligence is indeed a persistent feature of galactic ecology, then what responsibilities do we have as participants in this larger system? How should our growing technological capabilities be directed to contribute positively to cosmic development, rather than merely serving narrow human interests? The answers to these questions might depend partly on what we learn from continued study of interstellar visitors. Each new detection provides additional data about the kinds of processes that operate between stellar systems and the role that intelligence might play in shaping cosmic evolution. The chemical signatures we decode, the physical properties we measure, and the behavioral patterns we observe all contribute to our growing understanding of how matter, energy, and information flow through the galaxy. But perhaps the most significant discoveries lie ahead of us. The detection capabilities we're developing, the analysis techniques we're refining, and the theoretical frameworks we're constructing are all preparing us for revelations that could fundamentally transform humanity's understanding of its cosmic context. The next interstellar visitor might carry with it evidence that resolves long-standing puzzles about the nature of intelligence in the universe. Such discoveries would have implications that extend far beyond academic astronomy. The recognition that we're part of a larger community of intelligence, whether biological or technological, would influence how we approach questions about space exploration, planetary protection, and our responsibilities as a potentially spacefaring species. The knowledge that intelligence has been shaping cosmic evolution for billions of years would provide new perspectives on humanity's role in this ongoing process. Yet even as we prepare for such revelations, we must also consider the possibility that the universe might be far stranger than our current theories suggest. The interstellar objects we're studying might represent phenomena that transcend our understanding of physics, chemistry, and biology. They might be messengers from realms of reality we haven't yet learned to perceive. The implications of such possibilities push us toward a more humble and open-minded approach to cosmic exploration. Rather than assuming that our current scientific frameworks provide complete descriptions of reality, we must remain prepared for discoveries that could revolutionize our understanding of what's possible in the universe. The interstellar visitors streaming through our solar system might be preparing us for encounters with aspects of reality we never imagined. This openness to radical possibilities doesn't require abandoning scientific rigor or accepting extraordinary claims without extraordinary evidence. Instead, It demands that we develop more sophisticated methods for evaluating anomalous observations and more flexible theoretical frameworks for incorporating unexpected discoveries into our understanding of cosmic evolution. The challenge is maintaining the delicate balance between healthy skepticism and genuine openness to paradigm-shifting revelations. Too much skepticism might cause us to miss or dismiss evidence of phenomena that could transform our understanding of the universe. Too little skepticism might lead us to accept extraordinary interpretations of ordinary observations. The scientific community has been grappling with this balance as evidence accumulates about the unusual properties of some interstellar visitors. The case of Oumuamua illustrates both the power and the limitations of our current approaches to evaluating anomalous observations. Years of analysis and debate have refined our understanding of this object's properties, but haven't definitively resolved questions about its nature and origin. This ongoing uncertainty reflects the inherent challenges of studying phenomena that might transcend our current theoretical frameworks. When observations don't fit existing models, how do you determine whether the problem lies with the observations, the models, or our fundamental understanding of reality itself? The answer may depend partly on accumulating larger samples of similar observations. Individual anomalies can often be explained away as measurement errors, instrumental artifacts, or natural phenomena we haven't yet learned to recognize. But patterns of anomalies, especially those that appear consistently across different detection methods and analysis techniques, become much more difficult to dismiss. This is why the continued detection and study of interstellar objects is so crucial for resolving questions about their nature and significance. Each new visitor provides additional data points for testing hypotheses about interstellar object populations and their role in cosmic evolution. The statistical patterns that emerge from larger samples will help distinguish between genuine anomalies and observational biases. But perhaps most importantly, continued observations will help us develop more sophisticated frameworks for interpreting the unexpected. As we encounter more examples of unusual interstellar objects, we'll gradually build up the conceptual tools necessary for recognizing and understanding phenomena that don't fit our current theoretical expectations. This process of conceptual development might be just as important as the accumulation of observational data. The history of science suggests that revolutionary discoveries often require not just new observations, but new ways of thinking about what those observations mean. The interstellar objects we're studying might be teaching us new languages for describing cosmic phenomena we haven't yet learned to perceive. The implications of this possibility extend far beyond the study of interstellar visitors themselves. If we're indeed encountering evidence of phenomena that transcend our current understanding, then the conceptual frameworks we develop to interpret these observations might have applications throughout astronomy and physics. The new languages we learn for describing interstellar anomalies might help us understand other cosmic mysteries that have long puzzled researchers. This interconnectedness of cosmic phenomena suggests that the study of interstellar objects might serve as a gateway to understanding aspects of reality that we've never been able to investigate directly. The techniques we develop for analyzing these visitors, the theoretical frameworks we construct to interpret their properties, and the conceptual tools we create for recognizing anomalous patterns might all contribute to broader advances in our understanding of how the universe works. Yet for all the revolutionary potential that interstellar objects might represent, we must also acknowledge the possibility that they might simply be natural debris from ordinary astrophysical processes. The unusual properties we've observed might reflect our incomplete understanding of stellar evolution, planetary formation, and interstellar chemistry, rather than evidence of exotic physics or extraterrestrial technology. This possibility doesn't diminish the scientific value of studying these objects. Even if interstellar visitors turn out to be entirely natural in origin, they still provide unprecedented opportunities for understanding astrophysical processes we can't study any other way. They deliver samples from other stellar systems directly to our laboratories, enabling detailed analysis of material that formed under conditions we can't replicate or observe remotely. The chemical signatures preserved in these cosmic messengers are already revolutionizing our understanding of stellar nucleosynthesis, planetary formation, and galactic chemical evolution. Each new analysis reveals details about the diversity of environments that exist throughout our galactic neighborhood and the processes that connect stellar systems across vast distances and timescales. This empirical approach to understanding galactic evolution represents a fundamental advance over the purely theoretical and observational methods that have dominated astronomy for centuries. Rather than relying solely on remote sensing and computer simulations to understand how stellar systems form and evolve, we can now conduct direct chemical analysis of material from those systems. The implications are particularly significant for understanding planetary habitability and the potential for life to emerge and evolve in different stellar environments. The organic molecules we detect in interstellar objects, the isotopic ratios we measure in their constituent materials, and the trace element abundances we catalogue all provide clues about the chemical conditions that exist during planetary formation around other stars. This information is crucial for assessing the likelihood that life might arise in different types of stellar systems, and for understanding how biological evolution might proceed under conditions different from those that existed during Earth's development. The diversity we're discovering in interstellar object compositions suggests that the galaxy contains a much wider range of potentially habitable environments than our models predicted. But perhaps the most profound implication of interstellar object research is how it's changing our perception of connectivity and isolation in the universe. Rather than viewing stellar systems as isolated islands of matter and energy, we're beginning to recognize them as participants in vast networks of material exchange that operate over cosmic timescales. This interconnectedness operates on scales that dwarf any earthly network. Material ejected from stellar systems billions of years ago is still flowing through interstellar space, carrying with it the chemical signatures of worlds that may no longer exist. Meanwhile, newly formed planetary systems are receiving deliveries of processed material from throughout the galaxy, incorporating the chemical legacy of countless previous generations of stellar evolution. The recognition that we're part of this cosmic network has profound implications for how we understand our place in the universe and our responsibilities as an emerging technological species. The atoms in our bodies, the elements that make up our planet, and the organic molecules that enable life on Earth all participated in this vast circulation system before being incorporated into our local stellar environment. We are literally made from the recycled materials of the galaxy, temporary arrangements of cosmic matter that have achieved the remarkable feat of consciousness and self-awareness. The interstellar objects streaming through our solar system are our cosmic relatives, fellow travelers in the great circulation of matter and energy that connects all stellar systems throughout space and time. This perspective transforms our relationship with the cosmos from one of detachment and observation to one of participation and responsibility. We are not outside observers studying a foreign universe, but integral components of cosmic evolution, temporary manifestations of the universe's ongoing exploration of complexity and consciousness. The interstellar visitors that continue to arrive in our solar system serve as constant reminders of this deeper truth. They carry within them the memories of distant worlds and the chemical signatures of processes that occurred throughout galactic history. In studying them, we're not just investigating exotic astronomical phenomena, we're exploring our own cosmic heritage and preparing for our role in the ongoing story of cosmic evolution. As we stand on the threshold of discoveries that could fundamentally transform humanity's understanding of its place in the universe, we find ourselves confronting questions that seemed purely academic just a few years ago. The interstellar objects streaming through our solar system might be preparing us for encounters with realities we never imagined, carrying within them the keys to understanding cosmic processes that transcend our current theoretical frameworks. Each new detection brings us closer to revelations that could reshape our understanding of matter, energy, intelligence, and consciousness in the universe. The next interstellar visitor might carry evidence that resolves fundamental questions about the nature of reality itself, or it might raise new mysteries that push us toward even more profound transformations in our cosmic perspective. The journey of discovery continues, carried forward by the cosmic messengers that bridge the vast distances between stars, delivering to our doorstep the accumulated wisdom of billions of years of galactic evolution. In their silent passages through our solar system, these wandering worlds whisper secrets about the deeper nature of existence itself, inviting us to expand our understanding and embrace our role as conscious participants in the magnificent cosmic story that surrounds and includes us all. The profound realization that our solar system serves as a way station in this vast galactic circulation network forces us to confront an unsettling truth about the scale of what we're investigating. Every cubic kilometre of space within the orbit of Neptune potentially contains traces of material that originated in stellar systems scattered throughout our galactic neighbourhood. We're not just studying isolated visitors from distant stars. We're examining the physical evidence of a cosmic ecosystem that operates on scales so vast, they challenge our capacity to truly comprehend their implications. Consider what this means for our understanding of cosmic time and causality. The interstellar object that passes closest to Earth tomorrow might carry within its chemical matrix the fossilized signature of supernova explosions that occurred before our solar system even formed. Isotopic ratios created in stellar cores billions of years ago could be preserved in crystalline structures that have survived journeys lasting longer than complex life has existed on Earth. This temporal layering transforms each interstellar visitor into a kind of cosmic archaeological artifact, preserving multiple epochs of galactic history within the same physical structure. Advanced analytical techniques are revealing that individual objects often contain materials that formed at different times and in different stellar environments, suggesting complex histories of aggregation, disruption, and reassembly that occurred during their interstellar journeys. The implications become even more staggering when we consider the information density that these objects might represent. If the chemical processes that occur during stellar evolution and planetary formation are sufficiently complex, then the molecular arrangements preserved within interstellar debris might encode detailed information about the physical conditions that existed in their birth systems. We might literally be holding libraries of cosmic history in our hands, written in a chemical language we're only beginning to learn to read. This perspective opens entirely new approaches to understanding galactic evolution and the prevalence of complex chemistry throughout the universe. Rather than relying solely on spectroscopic observations of distant stellar systems, which provide only integrated measurements averaged over vast volumes of space, we can now conduct detailed forensic analysis of individual samples that preserve specific formation histories with unprecedented resolution. The forensic analogy is particularly apt because the challenges we face in interpreting interstellar object compositions are remarkably similar to those encountered in criminal investigations. We have physical evidence that clearly indicates something significant occurred. But determining exactly what happened requires painstaking reconstruction from subtle clues that might have been modified or contaminated during the intervening time period. The contamination problem is particularly acute for interstellar objects because they've spent millions or billions of years exposed to cosmic rays, solar wind particles, and the complex chemistry of interstellar space. These processes can alter surface compositions, modify isotopic ratios, and create new molecular arrangements that might obscure or mimic the original formation signatures we're trying to detect. Advanced space weathering models are being developed to account for these modification processes, but the complexity of the chemistry involved makes it extremely difficult to reliably reverse engineer the original compositions from the altered materials we observe today. It's like trying to reconstruct a faded photograph from a copy that's been repeatedly photocopied, each iteration introducing new distortions while preserving only fragments of the original information. Yet despite these challenges, the chemical signatures we're detecting are revealing patterns that provide genuine insights into the diversity of stellar environments throughout our galactic region. Certain types of isotopic anomalies appear consistently in objects that show other evidence of formation in particular kinds of stellar systems, suggesting that we're beginning to recognize the chemical fingerprints of different categories of stellar evolution. The statistical analysis of these patterns is becoming sophisticated enough to make predictions about the types of chemistry we should expect to find in objects originating from specific galactic regions. When new interstellar visitors are detected, their preliminary orbital characteristics can provide clues about their likely origins, which in turn generate predictions about their chemical compositions that can be tested through spectroscopic analysis. This predictive capability represents a fundamental advance in our ability to understand galactic chemical geography. Rather than simply cataloguing the properties of individual objects as they're discovered, we're developing theoretical frameworks that can relate chemical compositions to stellar environments and formation histories. These frameworks are beginning to reveal the underlying organization of chemical processes operating throughout our galactic neighborhood. But perhaps the most intriguing aspect of this emerging understanding is how it's revealing previously unrecognized connections between seemingly unrelated astrophysical phenomena. The chemical signatures preserved in interstellar objects are providing new insights into stellar nucleosynthesis, supernova explosion mechanisms, and the physics of planetary formation processes. Observations that initially seemed to be purely descriptive catalogues of exotic chemistry are turning out to have profound implications for fundamental physics. The isotopic ratios we measure in interstellar debris, for example, are providing new tests of theoretical models of stellar evolution and nucleosynthesis. The relative abundances of different elements are revealing information about the sequence of nuclear reactions that occurred in stellar cores, the efficiency of various fusion processes, and the mechanisms by which processed materials were ejected into interstellar space. Tonight, as we drift towards the quiet embrace of cosmic contemplation, we find ourselves standing at the threshold of a profound transformation in humanity's understanding of its place among the stars. The interstellar messengers that continue to stream through our solar system carry within them more than just chemical signatures and physical anomalies. They bear witness to a universe far more interconnected, dynamic, and mysteriously alive than we ever dared imagine. In their silent journeys across impossible distances, these cosmic wanderers whisper secrets that may forever change how we see ourselves and our destiny among the infinite depths of space and time. I wish you had an amazing time with me here at Boring Science. I wish you a very good night. I will see you tomorrow as always. Until then, stay curious and keep wondering. Cheers.